So once again, welcome back. Last lecture, we talked about distribution of primes a little bit. Today we are going to discuss some more result on it. That how we can estimate a prime. Okay. Estimation of prime means that suppose if you are denoting the first prime, very first prime by P1, and that is a 2, and then the second prime that is let us say this is P2, denote it, and this is 3, and the next prime P3 is going to be 5, and P4, the next prime is going to be 7. Okay, so it continues. So thing is that a natural question is that whether can we get some numbers, for example, m, such that pk is always less than or equals to m. So that is the question. So that is we want some upper bounds for this. Okay, if you put them in one set, for example, 2, 3, 5, 7, them some set. Suppose we are keeping them in capital P. So we are interested if there is any upper bound for this. Okay. Okay, let us see. So there is a result, and that result is not so sharp. Not so sharp means that if you write like that 2 is less than 100 or some 1000. Okay, so this inequality is not so strong in equality. Okay, if you write like this, x this is less than 3, so this is a much better inequality rather like writing 2 is less than 1000. Of course, there are so many numbers between 2 and 1000 which are greater than 2. Okay, so the next result is the nth prime. The nth prime, let us denote it by Pn, satisfies Pn is less than or equals to 2 to the power 2 n minus 1, n is greater than or equals to 1. So this is the result or prediction. Of course, if you see this, you can write a theorem or you can write a theorem. So if you see some point, for instance, let us see if it try to write P1, then P1 equals to, you know, that is 2. But if it put here n equals to 1, then you are going to get this right hand side here. So you are going to get 2 and 2 to the power n minus 1, that is 2 to the power 0, and 2 to the power 0. So this is equals to what? This is equals to 2. All right. And P2 is 3, and 2 to the power 3 and minus 1, that is 2. So 2 to the power 2, that is 4. 2 to the power 4 is what? 16?
16.
Yeah. So P2, which is a 3 and less than 16. Okay. And this 16 is nothing but 2 to the power 2. Okay. 2 to the power 2 to the power 2. All right. That is 2 to the power 4. You can write. And let us see more. P3 is 5, or let us P3 is 5. And in case 2 to the power 2 and 5 minus 1, that is 5 minus 1, I'm sorry, 2 to the power 2 to the power 5 minus 1, that is 4, 2 to the power 4, here it will come. So we will get what? 2 to the power 16, and this is a big number, you know. So there is huge difference between P3, that is 5, and 2 to the power 16. There is a huge difference. Okay. So as n increases, the difference between Pn and 2 to the power n minus 1 widen. Okay. So if you see, for example, is it okay? I don't know if I'm doing right. Here 2 to the power. Okay, I did mistake. 2 to the power P3 is there, so here should be 3. That is 2 here should be. And here I think I did mistake. 2 to the power P2 and 2. This should be 2 only, not 2 to the power 4. Okay, 2 to the power 2. That is 4. All right. And P2, that is this 4 and this is less than. Sorry, P2 is less than 4. Okay. Okay, let me erase everything. By mistake, I took the values. So here P2, so n is 2. So 2 to the power 2, 2 to the power here 2 minus 1. So we have a 2 to the power 2 here. So this is a 4. Sorry, this is less than. This is less than, and P2 is nothing but 3. All right, and then P3 is 5, and 5 is less than 2 to the power 2, and this is 3 minus 1, that is 2. So 2 to the power 4 we have. So here 16. Similarly, P4 is 7, and 7 is less than 2 to the power 2 to the power 6. Okay. So here the value is what is there? 2 to the power, I guess 62 to the power 64 or what? No, 2 to the power 8. I think I'm writing here 7. This is 3. Huh? This is 3. 2 to the power 8. Again and again, I'm choosing this value. So 2 to the power 3. No, 2 to the power 8 it became. Okay. And 2 to the power 8 is 256. So now see, here is 7 and here is 256. So there are huge difference. There is huge difference between PK and this value, or PN and this value. Okay. So this is not very good estimation if we say. So we can say Pn is less than or equals to 2 to the power 2 to the power n minus 1, where n is greater than or equals to 1, is a weak estimation. Is a weak estimation. Is a very weak, or we can write very weak estimation. Okay. But still we can prove this. So let us have a proof of this, and then later we can see more results on it. So proof. We will use induction. We use induction. In fact, mathematical induction. What I mean to say, induction on n to prove this result. You know what we do when we use a principle of mathematical induction. Actually, what we do, we first there is some statement is there, or some inequality is there, or some expression is there. So what we do, if we are using mathematical induction on n, so we used to take what? We used to first consider n equals to 1, and then we assume there are two kind of things. We assume, we first verify this, assume this is true for n equals to k, okay? Then prove, what we prove? We prove the result is true for n equals to k plus 1, 2, okay? So this is the one thing. Another one, verify for n equals to 1, and then assume the result is true for n equals to 2, 3 up to k, and then prove for n equals to k plus 1. So this is sometimes called a strong mathematical induction. Actually, in this, we are considering verification on n equals to 1. And then we are assuming that this is also true for n equals to 2, 3, and up to k. Okay, so we are in fact using all these things for n equals to 1, n equals to 2, n equals to 3, up to n equals to k, and then proving this one. Here what we are doing, we are verifying for n equals to 1, and then assuming that n equals to for n, this is true for n equals to k, and then with the help of these two only, we are proving that this is also. So thing is that here we have k things to prove the result for n equals to k plus 1. But here what we have, only two things. Here we have k things, okay, but here only two things. With the help of these two, we are proving that the result is also true for k plus 1, okay. And sometimes this is also called a second principle of mathematical induction, this one. So let us move further. Is it okay? Hello?
Yes, sir.
Yes, sir.
So let us, until now we have not started the proof. So let us move to proof. So clearly, one thing is very clear, that the result is true clearly for n equals to 1. We have p1 equals to 2, and 2 to the power 2 to the power 2 to the power 1 minus 1, that is 2 to the power 1. This is equals to 2. All right, this equals to 2, and p1, this is less. This is equals to, in fact, less than or equals to 2. Fine. Thus, the result or inequality is true for n equals to 1. Now we assume that the inequality is true for inequality is true for n equals to 2, 3 up to k also. Okay, so we have verified that the result is true for n equals to 1, and similarly we can also verify for 2, 3, maybe a few For few initial values of n, we can verify, but for the rest numbers, we can assume based on our previous experience or verification. Okay, so that is what this will give us. That is pi is less than or equals to 2 to the power 2i minus 1, where I takes value 1, 2, 3 up to k. Okay. So we have these many primes. Okay. These are the values pk primes we have considered initially. Now P1, P2 dot up to Pk plus 1. So we are taking product of these primes P1, P2, P3 up to Pk and then adding 1 must be divisible by some prime P uh, which cannot be among pi. This is because this number is P1, P2, P3 up to Pk, they are all natural number. They are, in fact, yeah, they are primes, and so natural number. And when we are taking the product and adding 1, they are going to be a natural number, certainly. And this is going to be greater than 1. Okay. So anything, if you take this much only, then each pi is a divisor of this P1, P2 up to Pk. Each pi is a divisor. And because pi's are prime, so therefore there will be no factor of them. Okay. And just we are adding 1. So any number, which is any number or any prime p, which divides this product cannot be among these. Okay. Uh, if it happens, so it also divides what? 1. Okay, which is not correct. And this cannot be, which cannot be among pi. For then I want to say, if it happens, suppose p is among some pi's. Okay, so for then p should divide 1, and which is absurd. Okay, which is absurd. You know why? Because if suppose p is some, p is equals to some pj. Okay, and j is between 1 to k, sum. Okay, and this p divides what? P1, then p divides P1, P2. Here somewhere pj is there, and then pk is there. Okay, if this also divides this one, fine. Okay, because p is equals to, this is pj, this is pj, p equals to pj. And also, since p also divides this product, p also divides p1, p2, and pk, pj is also there. Okay, pj plus 1. So this implies what? This implies that p should also divides 1. So this is not correct. So this is what I have written above. Okay. For example, if you take just like you take product 2, 3, 5, suppose 7 you are taking. Okay, and you are taking prime 3, and 3 divides this number. Fine. And you are telling also that 3 divides 2, 3, 5 into 7. and you are adding 1 here. Okay, you are adding 1 here. If at all, sorry, let us not write here 1. Let us write here some number a. Okay, so if at all this this divides, this 3 divides this product and plus a, so a has to be some multiple of 3. All right, but here we have 1. Okay, it means 3 should divide 1, which is not possible. Okay, so let us move further. And now certainly because of p, this p cannot be among p1, p2 and pk, so certainly this p is going to be greater than or equals to pk plus 1. Okay, so pk plus 1 is less than or equals to p, and this p is this pk plus 1, that is another prime which is next to this pk. Okay, we have kept them in increasing order, p1, p2 and pk. So this p must be next prime. Okay, it may be pk plus 1, pk plus 2, pk plus 3 or any prime like this. Okay, and this p is less than or equals to p1, p2, p3 and up to pk plus 1 like this. And each pi you see from here, this one is less than 2 to the power I minus 1. Okay, so this pk plus 1 less than or equals to p less than or equals to p1, p2, pk plus 1, and this should be less than or equals to 2 to the power 0, 2 to the power 1, 2 to the power 2, and it continues 2 to the power k minus 1 and plus 1 here. Okay, so because they are product and base in each case is same, so we can write 2 to the power. This is a 1, and then this is 2, this is a 4, and then it continues 2 to the power 2 to the power, sorry, 2 to the power k minus 1, 2 to the power k minus 1, and then here plus 1. And in the power of 2, we have a geometric series, finite geometric series. Okay, and then we can write their sum 2 to the power k minus 1 like this. And then a plus 1 also. And here we can write a 2 to the power k divided by 2, 1 by 2 and plus 1. This is not in power, but let me. Oh, sorry. What happened? This we can write like this by 2 and then plus 1. Fine. So this is certainly is going to be less than or equal to 2 to the power k. Okay. So because of here we are doing half of this number and adding 1 only. Fine. So this will be great. So this quantity will be always less than this quantity. Okay. So it means what? That this means that 1 is true for n equals to k plus 1 also. This completes the induction or proof. Okay. One thing is that when we are applying principle of mathematical induction, so actually what we are doing, you see, just for the sake of knowledge, we have verified it for n equals to 1, okay, and then let us make a set. The result is true for n equals to 1, fine. So let us keep the 1 in this set. And then we have assumed this is also true for 2, n equals to 2, 3, and up to k. So let us keep these numbers for which we have assumed the result is true here, 2, 3, up to k. Fine. And then we proved what? The result is also true for k plus 1. This is also true for k plus 1. So we are continually uh, uh, keeping those numbers for which the result is true in this set, in the set S, okay? And then since when we assumed that this is true for k, and then we are assuming that this is also true for k plus 1. So certainly because this result is true for k plus 1, so this is the result is going to be true for k plus 2, and hence for k plus 3, and this will continue, okay? This will continue. And because this is endless process by the piano axiom, the piano axiom says that if there is a number, a natural number n belongs to n, then n plus, that is n plus 1, is also going to be in the set n. So this is what piano axiom says. In short, I'm telling. So if there is k plus 3, then k plus 4 is also going to be there, k plus 5 is also going to be there, and this will continue infinitely, okay? So this will give us what? The set of natural number. So actually with the help of a principle of mathematical induction, we are doing what? We are verifying and simultaneously constructing the set of natural number. All right. Should we move further? Let us see. Next result is that there are infinitely many primes of the form of the form 4n plus 3. So let us prove this result. Actually, there is no formula with the help of which we can determine all primes. So if someone is giving you a number, so it is very difficult to say whether if number is sufficiently large, it is very difficult to say that the number is prime or composite, unless it is even. So in case of even, we easily determine that this number is a composite. But if the number is odd, then we cannot say. For example, if you have been given 9, so you cannot say that this is a directly. Oh, this is a odd, so this is a prime. No, no. 5 is also odd, but this is prime. 9 is composite, but odd. Okay. 13 is odd and prime. Fine. 15 is odd, but non-prime. So these are the things. So there were so many development to determine whether a number of a particular form is prime or non-prime. So in this direction, there is this result which says that the number which are of the form 4n plus 3 is going to be prime. So thing is that if you have been given some number, so there is a one way. This is not the final way that if it is deciding that then the number will be prime, otherwise not prime. Okay. But certainly, if some number you are when you are you can keep this that number in this form 4n plus 3, then that number is certainly going to be a prime number. Okay, so let us see how we can prove this result. So in contrary, let us assume in contrary, let us assume that there are only finite primes of the form no, let us suppose finite primes, say p1, p2, p3 up to pk. So let us construct another number with the help of this prime. Let m equals to 4 p1, p2 and up to pk and minus 1. So we can write it, let us take 4 common. So we can write p1, p2 up to pk. Okay, and then we can write minus 1 plus 3 like this. Okay, minus 1 plus 3. So this is equals to 4q plus 3, where q is p1, p2 up to pk minus 1. So with the help of those finite primes, we have constructed a number m, and we have written that m in form of 4q plus 3. So certainly this, because you see p1, p2, pk, they are primes, and then you are subtracting 1 from here. Okay, and okay, subtracting 1 from here, and you are multiplying it with 4. Fine. So this is going to be an even number, and you are adding an odd number, so this is going to be an odd number finally. So m is an odd number. Okay, so here m is an odd number. So its divisors are of the form either 4q plus 1 or 4q plus 3, like this. Are you getting? Because m odd, so its divisor will be odd of this form, either this 4q plus 1 or 4q plus 3. Okay. So now let us see if each prime p, if each prime p which divides m has the form 4q plus 1, then their product will be of this form only, okay, and And so M also will have the same form. I'm explaining it to you. Let us see. So what I'm trying to say that if there are numbers, suppose I'm writing for m plus 1, okay, divides this m, not let us not write m, but let us write here p, or let us write here p, 4p plus 1, okay. And another, suppose another divisor is there for q plus 1. This q is not same as what I have written before. So what we can write? Let us multiply. When we multiply it, this is we are going to get for 16q square plus 4q plus 4p plus 1, like this. And then you can take 4 common. So 4q plus 4q square plus 4 plus p plus q. This is plus 1. So this is 4r plus 1. Okay. So product of any two numbers of this form is going to be another number of this form. So what I'm trying to say, if p, suppose this is some prime, okay, which divides m, is of this form 4p plus 1, okay, and suppose each divisor of m has this form. So suppose one divisor has this form, another divisor has this form, can be written as like this, okay. Then all these product of all these is going to give us exactly m, okay. And then when we are taking the product of these divisors, we should get a number of the form m, and m is of the form 4q plus 3. But when we are taking their product, we are getting a number of the form 4r plus 1. So therefore, every divisor or each divisor of m cannot be of the form 4q plus 1. Is it clear to you?
No, sir.
Not. Let me again explain it again. So what I'm trying to say that m is our number, and we are trying to find the divisors, okay. And this divisor p has the form either 4q plus 1 or 4q plus 3. So I am assuming that every divisor has this form. Fine. पक्का कोई दिक्कत नहीं इसमें. देखिए तीन पॉसिबिलिटीज हैं, या तो सारे डिवाइजर इस फॉर्म के होंगे, या फिर सारे डिवाइजर इस फॉर्म के होंगे, या कुछ डिवाइजर्स ऐसे होंगे, कुछ डिवाइजर्स ऐसे होंगे. आर यू गेटिंग? हेलो,
Yes, sir.
आर यू गेटिंग व्हाट आई एम ट्राइंग टू से? Because m is odd, so odd numbers can be written as either in this form or in this form. Okay. Hello.
Yes.
So their divisor will be of this form, either this or in this form. Fine. All right. So if every divisor of m has this form, then we will be considering one case. Other case may be every divisor may have this form, or some divisors are of this form and some of are this form. Okay. So we are first considering that suppose every divisor has this form. Okay. Is it okay? And then we are proceeding. So if every divisor has this form, so we are writing 4q plus 1, 4q2 plus 1, like this, 4q3 plus 1. and so on. Each divides m. Fine. Each divides m. और सारे m के डिवाइजर इसी फॉर्म के हैं, 4q+1 4qi+1 इस फॉर्म के, पक्का? तो इनका जो प्रोडक्ट लेंगे 4q+1 एंड दो का मैं लेकर के बता रहा हूँ 4q2+1 एंड दिस इज गिविंग अस 4 टाइम्स q1 q2. ओके, आप मल्टीप्लाई इसको करेंगे तो 4 16 q1 q2 आ जाएगा प्लस 4 एंड 4 सॉरी q1 आएगा एंड प्लस q2 आएगा एंड देन यू विल बी गेटिंग व्हाट दिस. सो जो डिवाइजर्स उनका प्रोडक्ट किस फॉर्म का आ रहा है हमारे पास, 4 इक्वल्स टू 4 r+1 टाइप का आ रहा है, ठीक है? जबकि m किस फॉर्म का है, 4m+3 है ना? हेलो, 4q+3 टाइप का है ये. हेलो.
Yes, sir.
For example, you take some number, सपोज 4m+3, m की वैल्यू सपोज मैं 10 रखता हूँ, तो 44+1 रख लिया मैंने, ठीक है? तो 3 कर देते हैं, 3 कर देते हैं, ये हो गया कितना, 47 हो गया. 47 फॉर एग्जाम्पल मैं कर रहा हूँ. और यहाँ यहीं से हमें लेना पड़ेगा. पहले प्राइम, कुछ प्राइम ले लेते हैं, ठीक है ना? P1 P2 P3 ऐसे करके प्राइम ले लेते हैं. I don't know why you are not able to understand. अब इनके अगर सारे डिवाइजर का प्रोडक्ट निकालोगे तो ये नंबर आना चाहिए कि नहीं आना चाहिए, आप ये बताओ. हेलो. हेलो. हेलो.
यस सर.
आप बोलते भी नहीं हो कुछ. सारे सारे डिवाइजर्स हमने इस फॉर्म के लिए है ना, कंसीडर किया कि सारे डिवाइजर्स इसी फॉर्म के हों. तो ऐसा ही और भी आप डिवाइजर्स में मल्टीप्लाई कर लो तो हमेशा यही फॉर्म आएगा, समझ रहे हो आप, है ना? हमेशा यही फॉर्म आएगा. तो ये तो फॉर्म इसका नहीं है ना, m का फॉर्म नहीं है ये 4q+3 के फॉर्म का नहीं है ना? तो सारे डिवाइजर्स इस फॉर्म के नहीं हो सकते. समझ में आया कि नहीं? हेलो.
यस सर.
Okay, so some divisors must be of the form 4q+1. Hence, m must be divisible by at least one prime p of the form 4q+3. 4q+3. सो एक पॉसिबिलिटी हम लोगों ने डिस्कार्ड कर दिया कि सारे डिवाइजर्स इस फॉर्म के होंगे, ठीक है ना? हाँ, कुछ डिवाइजर्स इस फॉर्म के होंगे, कुछ डिवाइजर्स इस फॉर्म के होंगे, ठीक है ना? तो फिर दोनों का प्रोडक्ट आप निकालोगे ना तो 4q+3 टाइप का आएगा. आप कंप्यूट करके देख लीजिए. 4q+1, सपोज q1+1 एंड देन 4q2+3. सो ये कितना हो गया, 16 q1 q2 प्लस 4 एंड 3, आई मीन 12 q1 प्लस 4 q2+3 इस फॉर्म का. देखो अब 4 कॉमन ले सकते हैं आप, 4 q1 q2 प्लस 3 q1 प्लस q2 एंड प्लस 3 लाइक दिस. सो ये किस फॉर्म का आ गया, 4s+m टाइप का आ रहा है, सॉरी 4s+3 टाइप का आ रहा है. ये किस फॉर्म का है, m की फॉर्म का है, ठीक है ना? m किस फॉर्म का है, 4q+3 टाइप का. सो एटलीस्ट एक फैक्टर इसके डिवाइजर में, m के डिवाइजर में एक फैक्टर क्या होना चाहिए, 4k+3 होना चाहिए, 4q+3 होना चाहिए, इस फॉर्म का होना चाहिए. Okay, so by our assumption So by our assumption, if P equals to Pi for some I divides 4 divides 4 P1 P2 Pk minus M, that is P divides 4 P1 P2 up to Pk minus M, or 4 P1 P2 Pk and minus 1. This is equals to, from here is equals to 4 P1 P2. Okay, once we subtract M from here, so here we will be getting what? My 1. Okay, so this means this is 1, this is 1. Okay, so this implies that P divides 1, and this is not possible. Okay, so this is not possible. So it means ये जो हम डिवाइजर्स ले रहे थे कुछ इस फॉर्म के आ रहे थे, एटलीस्ट एक तो इस फॉर्म का था, बाकी किस फॉर्म के हो सकते हैं? 4q+1 की फॉर्म के हो सकते हैं। ऑलराइट, बट ये डिवाइजर्स जो हैं, ठीक है ना, ये जो प्राइम्स हैं 4q+1 या 4q+3 टाइप के प्राइम्स जो हैं, जो इसको डिवाइड कर रहे हैं, ठीक है ना, इसको डिवाइड कर रहे हैं, ये इसमें से नहीं हो सकते। और क्यों? क्योंकि अगर ऐसा हुआ, इसमें से Pi में से कोई सा एक हुआ, P1 P2 P3 अप टू Pk में से अगर कोई भी नंबर ऐसा हुआ, तो ये P जो है किसको डिवाइड करने लगेगा? इसको डिवाइड करने लगेगा, और इसकी वैल्यू कितनी है? 1 है, तो इसका मतलब P 1 को डिवाइड करने लगेगा, जो कि गलत है। ठीक है ना? तो वो जो डिवाइजर, चाहे 4q+ डिवाइजर्स जो हैं 4q+3 और 4q+1, इनके मिक्स टाइप के हैं कुछ डिवाइजर्स, तो वो Pi में से नहीं हो सकते। इसका मतलब क्या है कि वो कुछ और होंगे, इनसे ज्यादा होंगे, जबकि हमने क्या सपोज किया था? फाइनाइट नंबर ऑफ प्राइम्स सपोज किए थे। ठीक है ना? सो देयर आर infinite primes of the form 4q+3. So this completes the proof.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.